what if we are interested in the effect of x, a change in x, on the y variable? So we have this simple regression model in which we have one x variable and we have the y variable, and the internal validity requires that the estimate of the beta hat, which measures the causal effect, the linear causal effect of a change in x on the y variable, it should satisfy two requirements. And the first one is that our estimate of the slope is unbiased and consistent. What does that mean? Unbiasedness means that on average, our estimate centers around the true value of the slope. What does that mean? It means that if we have the true beta here, then if we redo our or if we perform one analysis, we take a random sample and we get a beta hat, then maybe this beta hat will be around here, but if we redo the analysis, maybe we get something on the low side of beta 1, but closer. And if we redo our analysis many times, then we will be able to create a histogram, which will, if we have a lot of analysis, then our estimate will be something like this. It would be normally distributed around the true slope, and this would be the distribution of beta 1 hat, and this unbiasedness means that the distribution of beta hat is centered on the true value of the beta. And consistent means that as beta hat or as the number of observations increases, then in the probability limit, our estimate of beta should be closer and closer to the true beta value. And this limit can also be written as probability limit as n goes to infinity, as our number of observations goes to infinity or increases a lot. Then our estimate should this probability limit of beta hat should be equal to the true value of the beta. So, which means that as our sample size increases, then this probability distribution of our beta hat should get more narrow. It should center more and more on the, or close in on the true value of beta. The probability limit, why we use the probability limit instead of the limit, is that we are not guaranteed that as we get more and more data, that our distribution gets more narrow, because we could be unlucky with our next draw, so it could widen for a moment, but on average it should close in on the true value. And the second requirement is that the hypothesis test should have the desired significance level. And what does that mean? It means that if we perform a hypothesis test and we want there to be alpha percentage change of a type 1 error, which means that there's a alpha percent chance of rejecting the null hypothesis, even if the null hypothesis is actually true, then if we choose that level, then the true probability should be that alpha. Okay, it should not be anything else. It should not be bigger or lower. So if we kind of make this test, then we know that this tail probability should be equal to our significance level. Okay, and equivalently, the confidence interval should have the desired confidence level. Okay, so if you have a 5% significance level, then you would have a 95% confidence level in your hypothesis test. So that's why it's really important for these requirements to hold. It helps us to build better models and trust our results. So there are seven threats to internal validity. One is the omitted variable bias. We have looked into that before. And the second is functional form misspecification. For example, you believe the relationship between one of the x variables and the y variables to be linear, but it's actually quadratic. Then you have a functional form misspecification. You have measurement error in the x variable or the y variable, and you can have problems with the sample selection. Maybe it's not random, but you believe it's random. And you can have simultaneous causality that x affects y and y actually affects x back. And you could have heteroscedasticity. We have looked into that before in the residuals. And you can have correlated error terms. Okay, so of these, the 5 first actually violate the first least squares assumption, which is the assumption that the expected level of the residuals is not dependent on the level of x. Okay, so no matter which level of x you look at, then the expected value of the residual should be 0. So the distribution of the errors should be centered around 0, no matter what x value you're looking at. And number 6 and 7, the heteroscedasticity of the error terms and the correlated error terms, they violate the second assumption for the least squares method, and that would be that these draws of x and y should be independent and identically distributed, which means that they should be draws from the same population, and they should not have an effect on each other. So one draw should not be able to affect another draw.